Everyone, so let's go ahead and let's solve this piece at 6. So let's look at the grain below. Each interface marked X. How will the grain grow or shrink? So let's go ahead and start to mark these. So I'm going to mark this as 1, 2, 3, 4, 5. I'm going to call this outside A. Actually, all the ones that are outside, I'm going to call this A, B, 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 B. So let's look at 1. So at 1, we know that the chemical potential of our sphere is equal to mu naught of unit plate plus or minus 2 gamma b bar over r. So that's what we're working with, an expression that we're kind of, so the positive or negative depends on our local curvature. So at 1, the chemical potential of A is actually less than the chemical potential at B. So you can kind of see here, if you look at it from the B perspective, we have positive curvature, A is negative curvature. So where are the atoms going to move? They're going to move from B to A. If we did our kind of curve, so G here, 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 here. So we go from B to A. So we jump from here to here. Those are kind of our Bell reaction curves. So chemical potential of A, so chemical potential of A would be equal to mu naught of our plate minus 2 gamma b bar over r. And then for B, it'd be the exact same thing, but this would be plus. So we go from high chemical potential to low chemical potential, so B to A. So that would push our boundary here. So this grain here would, that interface would move in this direction. So the grain here, the blue guy, would actually shrink at application. And that would be the same. So this whole discussion, 1, 2, or 1, 5, and 4, those are all the same. So this same kind of expression holds all the way there. For 2 and 3, it's the opposite. So for 2, we look at, so for example, 2, chemical potential of A is greater than the chemical potential of B. So everything just kind of flips. So now we're going from A to B, and then if we go from A to B, our G would be here, so here. So we're going from A to B, and then now we know we go from A to B, and that's going to push this interface out, so we're actually going to be growing in that location. So that's how it goes. So let's look at figure 2. Which grains will grow, which grains will shrink? How the growth rate scale of time. So we know that, actually, instead of growth rate, we know that R scales as t to the 1/2 for 2D grain growth. We know that it is modulated. R is like a function of, basically, R squared is a function of this m times our time. And we know that m has basically 1 over t and then an exponential of minus delta g a over kt. So temperature will increase essentially the slope there. So which grains are going to grow and shrink? So we know that our n equals 6 rule, so dr dt would be equal to 0 for n greater than 6 and less than 6. So we're going to grow here, we are going to shrink here. So let's count 1, 2, 3, 4, 5, 6, 7. So we are going to grow. Let's do so here, 1. This is kind of the same side actually. So you can count it as 6 or 7. 1, 2, 3, 4, 5, 6, 7, 8. So that's going to grow. Let's see here, 1, 2, 3, 4, 5, 6, 7. So that's also going to grow. And 1, 2, 3, 4, 5. Uh-oh, that one's going to shrink. So there we go. So let's go ahead and move on to number 3. Let's look at the snapshot of these 3D particle growths in figure 3. What particles, for the particles with the green arrows or with green arrows pointing on them, will they grow or shrink? Justify why. Alright, so let's take a look at this problem. So this is our average particle size. So this is equal, A is equal to A bar. So we know that from our 3D criterion that we know that if A is greater than A bar, we're going to grow. If A is less than A bar, we are going to shrink. So we can see, I'm going to go ahead and just put an S right next to them. So this one's going to shrink, shrink, this one will shrink, this one looks a little bit smaller, that'll shrink. This one looks to be about the same. So if A is equal to A bar, it's your dA dt is equal to 0. So it's not going to grow or shrink. So I'm going to say that one's not going to grow or shrink. And the ones that will grow, I'm going to say that my This guy will grow. I'm going to look and say that this guy is going to grow. And I think that's pretty much it. So let's go ahead and go back to our problem. So let's see. Which will grow or shrink? Got that. Justify y. We have our equation. Justified there. Again, we could also justify it from the perspective of chemical potential. So small particles. So again, chemical potential is controlled pretty much by our curvature, which is equal to 2 over r. So we go from high chemical potential to low chemical potential. If my radius is small, high chemical potential, the flux of atoms is going to leave those, and my large particles are going to grow. How will the growth rate scale with time? So we know that for A scales as t to the 1/3. What about temperature? So again, very similarly, we have for our equation for our average particle size A bar, it's kind of proportional to this d over t, and then there's a bunch of other prefactors, a cubed t. So again, d has d naught exponential minus qa divided by kt. That's our d, t. So as we increase temperature, our particles should grow. And what particles grow the fastest? So if you take the derivative of our equation here in lecture 6, so let's go over here. We took the derivative and we found that, where are we at here? Let's go back down. Took the derivative and we saw particles that grow the fastest is going to be equal to A equal to 2A bar. So let's go back to our Pset 6. And let's see here. A is equal to 2A bar. Those are the particles that are going to grow the fastest. Excellent. So let's go ahead and go on to problem 4. Explain the graph in figure 4 below. Why does the slope change as a function of temperature? How does the particle scale with time for each curve? So this is A cubed, so we know that we're dealing with Oswald ripening, i.e. 3D. So we just saw that, again, A bar cubed was proportional to D over T times time. So if I plot y versus this is my x, my slope is controlled by this, and just like we saw, right, that Arrhenius relationship will beat out this 1 over t. So as we increase temperature, our slope should increase. Excellent. So that's number 4. Let's go ahead, let's go and move back here. So, particle size change of time, we got it. So we see the same scaling, t to the 1/3. Which curve in figure 5 corresponds to homogeneous nucleation, which to heterogeneous? Also, where's nucleation dominated growth? Explain how you arrive at this conclusion via the critical amount of undercooling, which is easier, homogeneous, heterogeneous nucleation, energetically y. So, let's look at this curve. So remember, this is a function of t. So, what this curve is telling us is that this green curve can occur at hotter temperatures. So, first, let's kind of say for each of these curves, if I'm at high temperatures, diffusion is, so let's just look at this blue curve. At high temperatures, diffusion dominates. At low temperatures, I have basically nucleation dominating. So this curve can exist, my peak occurs at higher temperatures. So I need essentially less amount of undercooling. I need to be less cool in order to kind of reach my peak. So if I need less undercooling to even, actually, remember, so this is Tm. So my undercooling delta T is Tm minus T. So the larger amount of undercooling, the kind of harder it is to work. So this is heterogeneous, this is homogeneous. And what's easier energetically? Homogeneous nucleation. Why? Because, again, heterogeneous nucleation, we need less area, right? So we don't need to create surface area. We're always battling between our volumetric term, which pushes us to nucleate, versus our surface area. For homogeneous, we have to create the whole surface area, our 4 pi r squared. Heterogeneous, easier, same critical radii as we've kind of discussed multiple times in class, but that's what we're working with here. So let's see if we answer all the questions. So, figured out, we explained where nucleation is dominating, growth is dominating. How do you arrive at the critical amount of undercooling? Again, so our undercooling, we need less critical amount of undercooling than for homogeneous nucleation. So that's a lot of big difference in that. And we asked which is energetically, let's see, explain how this conclusion, got that, which is easier, homogeneous, heterogeneous because of the surface area term. Excellent. So that's number 5. So let's look at number 6. Derive an expression for the critical radius for homogeneous nucleation. Do the same for heterogeneous. Are the values the same or different? What size particles will grow or shrink? Derive expressions for the change that gives free energy for homogeneous and heterogeneous nucleation at the respective critical radii. Are they the same or different? Okay, so good old-fashioned derivation problem. So let's go ahead and let's open up Mathematica and let's kind of write out our expressions. So let's go ahead and go to our lecture 6. So let's look at our good old expression for homogeneous nucleation. Actually, let me go a little bit up here. Excellent. So this is our expression for homogeneous. So we have a volume term, which is equal to minus 4 times pi 1 minus 4/3 times pi times r cubed times del GV plus 4 times pi times r squared. Actually, that's the volume. So that's the volume term. We have area, which is equal to 4 times pi times r squared times gamma SL. So volume, so for homogeneous, is equal to volume plus area. So we got that right there. So if I want to find my critical radii, it's going to be d homo as a function of r. I'm going to set this equal to 0. So solve for set this equal to 0 for r. Oops. Let me get that value here. R cubed. That's why I want to get some, be a little bit careful on our expression. And there we go. That's our critical R value. So let's look at heterogeneous nucleation. It's the exact same expression with the exception of this S value, this S theta. So let's write our S theta. So we have S theta equals 1/4 times 2 plus cosine theta degree. I want to be in degree mode. Oops, and then times 1 minus cosine of theta squared, theta degree mode squared, and then I want to square that. So that's my S theta. So now I could just do, so my hetero equals homo times S theta. So if I do again, same exact expression, I see that d homo, d hetero, and same exact value. So our critical radii are exactly the same. But we were also asked for the energy here. So now I could do this, I could do hetero slash dot r goes to this value right here. And I could do my homo value right here. So let's go ahead and just do full simplify. So you could see that this value is going to be a slightly different than this one here. So what you're going to find when you actually plug this in and multiply everything out, this will be lower. So our heterogeneous nucleation is lower at this energy than here. So you can kind of see that from kind of our expression. Let's blow this up a little bit because I don't like ads. So you could see already, again, we're going to be lower because when we plug in any value here, actually, let's go ahead and plug in, let's say our R is that, and let's say our theta is 10 degrees. Anything that is, let's do that numerically. So we can see much lower, right, than this 16 over pi. So that's going to be, we'll do this numerically too, just so we can look at it. Yeah, so very, very different, much smaller, heterogeneous. We're going to be good to go. Excellent. So let's go ahead and see what's next on our problem set, what's left over. All right, so which particles will grow or shrink? So we know that if R is greater than R star, we're going to grow. If R is less than R star, we are going to shrink because our gives free energy increases here. So delta G will increase here, delta G decreases here. Let's see. Value's the same. Critical radius, so they were the same for the critical radius. Gives free energy. was lower for our heterogeneous nucleation, so lower. Excellent. Now we're going to look at essentially the growth of nuclei in figure 6, which particles grow, shrink, how the curve changes, heterogeneous. If we increase the amount of undercooling, how will this shift? So if this is, we know that this is equal to our R star. So here we know we're going to grow. Here we know we're going to shrink. If this was heterogeneous, it would look exactly the same location here. So this is be my hetero. If my delta T increases, we saw that our R star value, R star was equal to 2, actually let's pull it up. Was it 2 gamma SL, yeah, delta GV, divided by delta GV. We also know that delta GV is equal to delta HF, delta T, amount of our undercooling over Tm. So we know that if I increase my delta T, i.e. right here, increase my delta T, my R star is going to decrease dramatically because I want to grow more. So that curve could potentially look like this. And then if my delta T decreases, again, hotter, not colder, my critical radii is going to grow dramatically because of that inverse relationship. So it would look probably something like this. Again, this is saying if I increase my delta T, I could grow all of these particles more than the other particles there. So until I hit here, then these guys can grow. So again, more the system wants to evolve towards a solid, a crystal, a solid material when you're looking at this when the temperature is colder. That should make sense. So hopefully this makes sense, and hopefully this has been helpful to kind of check your problem set. So I'll see you in the next video. Thanks.